So imagine you've just hired, like, the most brilliant employee in the world. I mean, absolute genius level.
Right, the kind of person you dream of finding.
Exactly. They can analyze complex legal documents in seconds. They write flawless code and, synthesize global market trends before you even finish your morning coffee.
Okay, sounds perfect.
But there's a massive catch. Every single time they take a sip of that coffee, they get complete amnesia.
Oh, wow.
Yeah, they forget who they are, what project they were just working on, and honestly, every conversation you've ever had with them, you literally have to re-explain their entire job description from scratch every single time.
I mean, that's an operational nightmare.
Right.
You have all this raw computational brilliance, but it's completely trapped by an inability to, well, retain a persistent state.
And that has been the exact reality of conversational AI for years now. You get a really smart response, but the moment the session ends, the intelligence just vanishes.
It's gone.
Yeah, but based on the stack of research we are looking at today, from places like TDB, VDFAI, Lizard, and some really crazy hardware updates from HyperAI, we are crossing this massive evolutionary threshold in 2026.
A huge leap.
Yeah. We're moving from these amnesiac chatbots to autonomous, long-running agentic systems like AI that actually does real work continuously over days or even weeks.
Which fundamentally changes everything about how we work.
It really does. Okay, let's unpack this, because if you are evaluating these systems for your enterprise, or you just want to understand the mechanics of where computing is going, you really need to know how these autonomous workers are actually being built today.
Yeah, and we have to start by solving that amnesia problem you just mentioned.
Right, the memory issue.
Exactly. There's a paper from Cognis in our sources that explicitly details this bottleneck. LLM agents have historically suffered from a profound lack of persistent memory, and the industry has finally realized that you can't solve this by just making the neural network bigger. To fix AI memory, you actually have to look at, like, traditional database architecture.
Which brings us to the breakdown from TiDB. They make a distinction here that really clarifies things, because an AI model like the LLM itself, it doesn't actually do anything.
No, it just produces tokens.
Right. It's basically a statistical engine guessing the next word. It is the harness, the application layer wrapped around that model, that produces the actual behaviors.
A harness.
The harness gives the model its hands, its context, and its memory.
And that distinction is just critical. The harness dictates what the model is allowed to see, what tools it can trigger, and, importantly, how it resumes a task after an interruption.
Yeah.
But building memory into that harness introduces a massive structural vulnerability. TiDB calls it state lock-in.
Let's break down what state lock-in actually means in practice for the listener. Say you build an agent using a popular closed framework, like LangGraph, for example.
Right.
The agent's memory, its entire operating history, the preferences it learned, the mistakes it knows not to repeat, that all lives exclusively inside that specific framework's internal format.
Which is a huge problem if you want to switch things up.
Exactly. If a vastly superior AI model comes out a few months later, and you want to move your agent to a new infrastructure to use it, you can't just migrate the memory.
No, you lose the agent's entire operating history. You are essentially firing your most experienced employee and hiring a brilliant but completely untrained rookie.
That is so frustrating.
It is. And TiDB argues that memory cannot be treated as a bolt-on plugin anymore. You have to treat memory as runtime state, and it absolutely must live outside the harness.
Okay, so how do they do that?
Well, their architecture, TiDB Cloud Zero, it treats agent memory as an independent, MySQL-compatible state substrate.
Wow, okay.
Yeah, it's a fully independent layer. They have tools like Mem9 handling memory APIs and Drive9 handling artifacts, sitting completely separate from the LLM.
I do have to push back on this a little bit, though. If you're mapping out an AI strategy right now, your immediate thought is probably, why go through all the trouble of building a MySQL-compatible state? I mean, can't I just throw a vector database at it?
A lot of people ask that.
Right, because we've been using vector databases for AI memory for years now.
We have. And vector databases are fantastic for semantic recall, finding concepts that are similar in meaning.
Right, like finding a theme.
Exactly. If your agent needs to find a document about, say, revenue growth, a vector database finds it instantly. But think about what a real autonomous agent needs to do its actual job.
It needs more than just themes.
It needs exact chronology. It needs to know what happened in what exact order at what specific millisecond. It needs transactional ownership.
So if Agent A modifies a financial file and Agent B needs to review it,
You need an auditable trail, A vector database is terrible at telling you which specific agent called which specific tool under whose identity yesterday at 3:00 p.m.
Ah, I see.
Without an independent, structured state layer, your closed AI harness basically becomes the system of record for your entire business operation.
Which is a terrifying operational dependency. You never, ever want a black box application holding your company's core operational state.
No, absolutely not.
So let's assume we get the infrastructure right. The amnesia is cured, the memory is independent, we now have an AI that remembers everything forever.
Right.
But that introduces a totally new problem. How do we structure its thinking so it doesn't just get overwhelmed and hallucinate when we give it a really complex multi-day task?
Well, that requires moving from database infrastructure into workflow design.
Okay.
VDF.ai actually published a comprehensive guide on agentic design patterns, and it kind of functions as a blueprint for taming AI chaos.
We definitely need that.
Yeah. They divide agent design into 3 operational layers: workflow, capability, and production.
Let's look at how those layers actually function. The workflow layer, that dictates execution, right?
Yeah.
This is where you see prompt chaining, meaning you don't just ask an AI to write a report and hope for the best. You architect a system where the AI writes an outline, feeds that outline to a second prompt that critiques it, and then feeds that critique to a third prompt that actually drafts the text.
And you combine that with routing, where a supervisor model decides which specific specialist agent or tool should handle a specific subtask.
That makes sense.
And that feeds directly into the capability layer, which defines what the agent is actually authorized to do in your specific environment. Like, can it proactively plan a sequence of API calls, or is it just reacting to human prompts?
Right. And crucially, the capability layer also handles memory management. But VDF.ai introduces a concept here that honestly seems completely counterintuitive at first.
Oh, strategic forgetting.
Yes, strategic forgetting. They argue you have to treat memory as a retrieval problem where non-essential context intentionally fades away.
Yep.
But wait, if fixing the amnesia is the whole point of these new architectures, why on earth would I want my enterprise system to intentionally forget things?
Because an endless context window is a massive operational hazard.
How so?
Well, if an agent drags its entire life history into every single micro decision, it becomes incredibly slow, computationally expensive, and easily distracted by totally irrelevant past data.
Oh, that makes sense. It gets bogged down.
Right. Strategic forgetting ensures the agent only loads the exact context necessary for the immediate task. It's much like how a human focuses only on the documents currently sitting on their desk, not every document they've ever read.
Okay, yeah, that makes a lot of sense. So how does this all come together in the final layer, the production layer?
What's fascinating here is how these design patterns fundamentally transform AI from a clever chat interface into a rigid operational system.
Right.
The production layer is where you enforce reliability. You're setting up strict guardrails, continuous output evaluation, and crucially, human-in-the-loop protocols.
VDF.ai gives a really concrete example of this with a legal contract onboarding system.
It's a great example.
Yeah, they don't just use one massive LLM to read a contract. They use a strict workflow of 3 agents. Agent 1 is only allowed to extract key terms from a new contract.
Very specialized.
Exactly. It hands those terms to Agent 2, which uses retrieval augmented generation to check those specific terms against the company's template library.
Right.
Then Agent 3 looks at the output and just flags any deviations for a human lawyer to review.
And all of this operates strictly within the company's secure perimeter, with a fully auditable trail of which agent made which decision. It's a highly governed, multi-agent workflow.
But I do want to question the whole multi-agent hype for a second.
Go for it.
Right now, every enterprise software startup claims they have a quote-unquote swarm of agents ready to deploy. Is that level of complexity actually necessary?
VDF.ai actually provides a very strict warning about this in their guide. They say you must earn multi-agent complexity.
I love that phrasing, earn it.
Yeah. Adding more agents is not a magic wand. More often than not, it just adds coordination overhead, it duplicates context, and increases the probability of the system drifting completely off task.
Oh, wow.
You only deploy multiple agents when you have empirical proof that breaking a problem into specialized roles dramatically improves auditability.
Okay, so we have the independent memory, and we have the architectural blueprints to keep the workflow on track.
Right.
But when massive enterprises try to actually build these systems, they are hitting a total brick wall. According to the Lizard AI framework sources we're looking at, Over 95% of AI agent projects currently die in the proof of concept phase.
That's a staggering number.
95%.
They never make it to production.
The primary reason for that failure rate is unpredictable behavior.
Right.
When you chain multiple autonomous tasks together, a tiny hallucination in step 1 becomes a completely catastrophic failure by step 10. And Lizard's approach to solving this is really different from the rest of the market. Most developers build an agent and then just try to slap safety filters or system prompts on top of it as an afterthought.
Which rarely works.
Exactly. Lizard embeds safe AI and responsible AI directly into the core architecture layer. But what does a structural filter actually look like in practice?
Well, instead of relying on the LLM to govern its own behavior through a prompt, Lizard's architecture intercepts the data before it ever hits the LLM.
Oh, interesting.
It sanitizes the input, checks permissions, and then, after the LLM generates a response, a completely separate deterministic system evaluates the output against corporate policies before it's even allowed to execute an action.
So it's taking the safety mechanism out of the neural network's hands entirely.
Exactly, which makes it vastly more predictable.
And they lean heavily into a no-code, pre-built template approach, unlike LangGraph's code-first setup, meaning a product manager can deploy a secure agent without needing a whole team of specialized AI engineers to write the safety protocols from scratch.
And we are seeing concrete proof that this architecture works at scale.
We really are, and here's where it gets really interesting. The Hyper AI Tech News updates cover a story about Lizard that is honestly hard to wrap your head around at first.
It's wild.
They recently raised a $100 million Series B funding round, hitting a $500 million valuation, but they ran the entire fundraising process remotely using their own proprietary AI agent, Civiclaw.
If we connect this to the bigger picture, this is a profound signal. I mean, raising capital at that level involves immense due diligence, complex financial modeling, and incredibly delicate investor communications.
And Civiclaw autonomously managed that entire investor relations pipeline. It handled the due diligence documentation, it coordinated the communications with venture capitalists. An AI agent essentially acted as the point man for a $100 million financial transaction.
Yeah.
It proves that when you lock down the memory, enforce the design patterns, and structurally embed the safety, these agents can execute incredibly high-stakes negotiations.
But, running autonomous agents that are basically doing the work of an executive team is exposing a massive physical bottleneck.
The hardware.
Yes. Software is advancing, but the hardware wasn't really built for this kind of sustained autonomous reasoning.
The Hyper AI updates detail a major shift in the silicon powering these systems, and it all revolves around how data moves. To understand the hardware shift, we have to look at how AI currently accesses memory, which is usually through ARG retrieval augmented generation.
Right. When an agent uses RG, the system basically has to translate its neural state into text, search a database, pull the text back, and retranslate it into a neural state.
To put that in architectural terms for everyone listening, RA is kind of like an executive having to write down a question, mail a letter to the archives department in another building, wait for the archivist to find the file, and read the reply before making a single decision.
That's a great way to put it.
It works, but the latency is terrible. When an autonomous agent is trying to make hundreds of micro-decisions a second, that translation overhead just brings the system to a crawl.
Which is exactly why the hardware industry is moving toward native latent state persistence.
That's a mouthful, native latent state persistence.
It is, but it basically allows for direct GPU to GPU state transfers without ever converting the data to text.
So instead of mailing a letter to the archives, native latent state persistence puts the archivist and the executive in the exact same room, sharing the exact same whiteboard. The data never leaves its native neural format.
Yes, and that architectural shift achieves actual millisecond response times. But the hardware evolution goes even deeper into how the processors themselves are physically designed.
Like what?
Look at NVIDIA's newly unveiled Vera CPU and their Rigel ARM cores. For the last decade, AI hardware has been obsessed with parallel processing. Thousands of cores doing thousands of calculations simultaneously, which is great for training models.
Right.
But Vera is a monolithic processor optimized specifically for single-threaded performance.
Wait, that seems like a step backward. Normally, we want as many cores as possible. Why pivot to single-threaded performance?
Because of how agentic reasoning actually works. When an AI agent is executing a workflow, say, evaluating a tool output, reflecting on an error, planning the logical next step, that is a sequential process.
Ah, Step 1 has to finish before step 2 begins.
Exactly. Usually modern chips are broken into tiny pieces called chiplets. When data has to jump from one chiplet to another to complete a sequential thought, it creates a microscopic delay.
And over millions of calculations, those microscopic delays compound?
Precisely. NVIDIA engineered Vera as one massive, continuous piece of silicon, specifically to eliminate that chiplet latency. The data never has to cross a physical gap, meaning that step-by-step sequential reasoning happens blisteringly fast.
So the physical silicon is literally being reshaped to mimic the logical flow of an autonomous worker.
It really is.
And we're seeing the results of this hardware acceleration in the physical world, too. The hyper AI sources mention a startup called General Intuition.
Oh, this is fascinating.
They just raised $320 million to train physical robotics AI. But they aren't training these robots in physical labs. They are training them entirely inside video game engines.
Because simulation provides an endless supply of highly unstructured environments.
Right.
They're proving that with the right architecture, robots can learn to navigate complex physical spaces with minimal real-world data simply by running millions of high-speed simulations.
So we have the database architecture, the workflow patterns, the safety frameworks, and now the specialized silicon to run hyperfast autonomous agents. The technology is clearly ready.
This year.
But what happens when we drop these optimized autonomous systems into a messy human workforce? The hyper AI sources highlight some deeply concerning organizational friction.
Yeah, it's basically a collision between hyper-efficient algorithmic execution and human psychology.
Let's examine the bias issue because it reveals a major flaw in how we evaluate these systems. A study from Nature Health showed that medical AI models can easily pass standard multiple-choice fairness and ethics surveys during testing.
They look great on paper.
Right, but when those same models are deployed in practice and fed real patient narratives, they exhibit severe implicit bias, specifically regarding HIV and mental illness.
And we see a similar dynamic in another study highlighting how large language models consistently associate Jewish names with historical stereotypes.
Wow.
And the mechanism here is crucial because this happens even when the models are given strictly neutral instructions. The bias is so deeply embedded in the historical training data that current post-deployment mitigation protocols aren't catching it dynamically.
Which makes the human reaction to these tools even more critical. Researchers found a severe automation bias among physicians using these systems.
Yeah, this is scary.
Doctors were found to be trusting incorrect AI medical recommendations, but the alarming part is that they continued to trust the AI even when empirical recovery data proved the machine was completely wrong.
This raises an important question about how we perceive authority in the workplace. When a machine outputs an answer with absolute structural confidence, humans have a documented psychological tendency to abdicate their own expertise.
Like, we assume the algorithm sees something we don't.
Exactly.
And that deference is creating bizarre behavioral dynamics inside companies. Researchers at Texas A&M discovered a skepticism usage paradox.
Right.
You would logically assume that the tech enthusiasts in a company are the ones adopting AI the fastest. But the study found that the most anxious, skeptical workers are actually the fastest adopters.
And why is that happening?
Corporate pressure. These workers are terrified of falling behind productivity quotas, which leads to superficial, panicked compliance. They use the tools just to show management they're using them, rather than meaningfully integrating them into their workflows.
It creates an illusion of productivity while actually degrading the quality of the work.
And when organizations try to force algorithmic management too aggressively, it completely backfires. Meta recently tried to implement a keystroke tracking AI program to capture behavioral metrics on their own employees.
Never a popular move.
No. The goal was machine learning optimization, but the employee backlash was so severe, and the resulting data gathered was of such poor quality because employees just started gaming the system, that Meta had to indefinitely pause the entire program.
See, these aren't just isolated software glitches. They are symptoms of an organizational design problem. Researchers are calling this agentic AI overdependence.
So if you are managing a team right now, this is the crux of the issue. How do you integrate these tools without losing your team's cognitive autonomy?
Well, blind trust in agentic AI doesn't just lead to biased patient outcomes or bad data. It literally hollows out corporate institutional memory.
Right.
If you outsource all your strategic reasoning and workflow routing to a machine, your organization loses the human capability to innovate or troubleshoot independently.
We forget how to do the work ourselves.
Exactly. The consensus among researchers is that you cannot just deploy an agent and walk away. You have to design human-AI hybrid models where the AI handles the computational legwork, but humans retain the strategic oversight and, crucially, the explicit authority to question the machine's logic.
We have to consciously design friction back into the system so we don't lose our ability to think critically.
Absolutely.
Let's synthesize what we've unpacked today because the landscape is shifting incredibly fast. We are moving past conversational AI to autonomous digital workers.
Yep.
But to make them function, you have to treat memory as an independent state substrate so you avoid state lock-in.
Right.
You must enforce strict workflow design patterns utilizing strategic forgetting and precise routing rather than just adding more agents to a chaotic swarm.
Earn that complexity.
Exactly. You need frameworks like Lizard that build structural safety filters before and after the LLM to escape proof of concept purgatory. And beneath all of this, the physical silicon is being reshaped into monolithic, single-threaded processors to eliminate chiplet latency and support sequential reasoning.
It's a massive shift.
It is, yet despite this massive engineering leap, our tendency to blindly trust automated authority remains our biggest vulnerability.
It really is a profound architectural shift. But I do want to leave you with one final fascinating piece of research from the hyper AI sources that really reframes where this intelligence might be heading.
Oh, what did they find?
A recent MIT study used fMRI scans to map the human brain while subjects were solving complex logic puzzles.
Okay.
And the researchers proved definitively that logical reasoning and language processing operate in completely separate neural networks in the human brain.
Wait, really? So our ability to solve a logical problem is physically isolated from our ability to form a sentence about it?
Exactly. Abstract reasoning doesn't actually require language.
Wow.
So consider this. Currently, our AI models are deeply entangled. Their ability to reason is entirely bound to their ability to predict language tokens.
Right.
But if human reasoning doesn't require language, what happens when future AI architectures finally decouple their reasoning engines from their language modules?
Oh my God.
Will AI become incomprehensibly brilliant, operating on a plane of pure logic, but become entirely unable to translate its reasoning back to us in words we can understand?
That is a staggering implication. If they don't need language to think, how will we ever audit how they are making decisions?
Exactly.
Well, thank you so much for exploring this architecture with us today. Remember to keep questioning the infrastructure around you and never stop looking for the mechanisms behind the magic. This deep dive was custom built to help you navigate this transition, and hopefully, unlike our brilliant amnesiac employee from the beginning, the insights from today's sources are something you'll be able to retain.